July 1st, 2025, 420 million miles from the Sun, a machine in Chile catches something impossible. 3. Atlas enters our solar system moving at 137,000 miles per hour, faster than any interstellar visitor we've ever tracked. But speed isn't what makes astronomers nervous. It's the trajectory, the timing, the things that shouldn't line up but do. You've heard about comets before, dirty snowballs trailing dust and gas as they heat up. 3. Atlas doesn't behave like that. No tail. No spectral signatures of outgassing. Just a bright ball of light racing through space on a path that seems calculated. Harvard astrophysicist Abraham Loeb calls it anomalous. The European Space Agency calls it natural. NASA calls it unprecedented. But what the telescopes show changes everything we thought we knew about visitors from other stars. If you value documented space exploration and astronomical research like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the Harvard Smithsonian Center for Astrophysics paper, published July 21, 2025, in RSev preprint 250.7.12213 AG. And NASA's Asteroid Terrestrial Impact Last Alert System discovery data from July 1st, 2025. Now back to the information. 3. Atlas doesn't follow the rules. First rule broken: size versus brightness. When the Asteroid Terrestrial Impact Last Alert System spotted this object, the brightness signature suggested something 20 kilometers across. That's huge for an asteroid. Too huge. Based on what we know about interstellar space debris, we should find 1 million objects the size of Oumuamua before we spot one this large. The statistical probability is less than 1 in a million. Second rule broken: orbital alignment. 3. Atlas travels in a retrograde orbit, tilted just 5 degrees from Earth's orbital plane. Random objects from interstellar space should arrive at random angles. The chance of this precise alignment? 0.2%. Abraham Loeb calculated this in his paper published July 21, 2025. 0.2% means this happens twice in 1,000 random encounters. Third rule broken: planetary approaches. 3. Atlas will pass within 0.65 astronomical units of Venus, 0.19 astronomical units of Mars, and 0.36 astronomical units of Jupiter. The combined probability of one object approaching all 3 planets this closely by chance: 0.005%, less than 5 chances in 100,000. But here's where the story gets strange. 3. Atlas times its closest approach to the Sun for October 29, 2025. That date puts it on the opposite side of our star from Earth, when it's brightest and most visible. Perfect timing to hide any unusual activity from our telescopes. The James Webb Space Telescope captured 3 Atlas on August 6th, 2025, using its near-infrared spectrograph. The data revealed something unprecedented. Carbon dioxide comprises 80% of the comet's emissions. Water makes up just 20%. Normal comets show the reverse ratio. This chemical signature doesn't match anything in our solar system. Dr. David Jewett from UCLA, who led the Hubble observations, told NASA this represents an entirely new class of interstellar object. Hubble images from July 21st show another mystery. 3. Atlas has a teardrop-shaped cocoon of dust, but no traditional comet tail. The dust production rate suggests active outgassing, but spectroscopic analysis finds no evidence of the gases that should be escaping. The Very Large Telescope detected nickel vapor and cyanide gas starting July the 20th, but no iron vapor, unusual because nickel and iron typically outgas together from comet nuclei. By August 25th, 2025, hours. NASA's Spherex Observatory confirmed the carbon dioxide emissions were increasing as 3 tours Atlas approached the Sun. The comet was releasing 129 kilograms of carbon dioxide per second, 6.6 kilograms of water per second, 14 kilograms of carbon monoxide per second. These are the jet bursts, but they don't behave like normal comet jets. Normal comet jets follow predictable patterns based on solar heating. 3. Atlas shows something different. The bursts intensify in a steady progression that matches no known natural process. The European Space Agency's Marco Micheli used precise astrometric measurements to track the object's path. No non-gravitational acceleration detected yet, but that could change. Abraham Loeb's team analyzed the trajectory using Optimum Interplanetary Trajectory software. If 3 Atlas wanted to intercept Earth, the optimal arrival window opens November 21st to December 5th, 2025. The the delta V requirements for course corrections to hit Earth. Mars, or Jupiter, remains surprisingly low, under 5 kilometers per second through July. That's the speed of an intercontinental ballistic missile. The timing gets more suspicious. 3. Atlas was difficult to detect earlier because it approached from the direction of the galactic center, where dense star fields obscure faint objects. By the time astronomers spotted it, launching an intercept mission became nearly impossible. The last viable launch window closed in July 2024, a full year before discovery. If you value documented space exploration and astronomical research like this, subscribe. It's the best way to support our work. This information comes from peer-reviewed observations by NASA's Hubble Space Telescope, the James Webb Space Telescope, and the European Southern Observatory's Very Large Telescope, all published between July and September 2025. NASA's fleet mobilizes for continuous observation. Hubble will perform ultraviolet spectroscopy in November 2025 to analyze the comet's gas emissions and sulfur to oxygen ratios. Webb will observe again in December after perihelion passage. The transiting exoplanet survey satellite found evidence of activity dating back to May, 2 months before official discovery. The Swift Observatory detected water vapor sublimating from ice grains 4,000 to 10,000 kilometers from the nucleus. Europa Clipper and JUICE spacecraft will attempt to pass through 3 Atlas's tail in November. The Parker Solar Probe and Solar Orbiter will monitor the object during its closest approach to the Sun when Earth-based telescopes lose sight of it. These observations will test whether 3 Atlas exhibits any non-gravitational acceleration, the smoking gun for artificial propulsion. The scientific community splits on interpretation. Richard Moisel from the European Space Agency maintains all observations align with unnatural. Space-weathered comet showing weak activity. David Jewett from UCLA calls it clearly active but within normal comet parameters. Other researchers point to the statistical impossibilities in unusual chemistry. 3. Atlas moves too fast to be bound by our Sun's gravity. Its orbital eccentricity measures 6.141, the highest of any known interstellar object, higher than Oumuamua's 1.2 or Borisov's 3.4. This extreme eccentricity makes the trajectory appear almost straight rather than curved. The object will reach maximum speed of 68 kilometers per second at perihelion, 42 miles per second relative to the Sun. After October 29, it begins its journey back to interstellar space. But if the trajectory changes, if non-gravitational acceleration appears, if the jet patterns shift unexpectedly, we'll know we're dealing with something unprecedented. Dr. Jewett estimates 3. Atlas measures between 440 meters and 5.6 kilometers across. Hubble's resolution can't distinguish the solid nucleus from its dusty coma. The actual size remains classified based on how much dust the object produces versus how much light it reflects. Temperature readings show 3. Atlas began outgassing when it was still over 4 astronomical units from the Sun, farther than most comets start activity. The early outgassing suggests volatile materials more sensitive to solar heating than typical water ice. Carbon dioxide sublimes at lower temperatures than water, explaining why it dominates the emissions, but carbon dioxide doesn't explain the nickel vapor. Metallic emissions require temperatures above 900 degrees Celsius. 3. Atlas was nowhere near hot enough for natural nickel sublimation when the Very Large Telescope first detected it. The mechanism remains unknown. Congresswoman Anna Paulina Luna sent a letter to NASA leadership in August 2025, supporting Abraham Loeb's proposal to use the Juno spacecraft for closer investigation. Juno will pass within 53.6 million kilometers of 3 Atlas on March 16, 2026. Close enough for detailed sensor analysis, the proposed mission would test Loeb's technological hypothesis. If 3 Atlas shows artificial acceleration, electromagnetic emissions, or structured geometry, we'd have proof of extraterrestrial technology. If it behaves like a natural comet approaching the Sun, the mystery becomes one of unusual chemistry rather than artificial intelligence. Time runs out for Earth-based observations. 3. Atlas disappears behind the Sun in late October 2025. When it emerges, moving away from us at maximum speed, we'll have weeks before it fades beyond telescope detection. Any secrets it carries will vanish with it into the void between stars, unless something changes first. The Vera Rubin Observatory begins operations in 2025, designed to detect hundreds of interstellar objects over the next decade. If 3 Atlas represents a new class of visitor, we'll find more. But if it represents something else, something watching, measuring, calculating as it passes through our neighborhood, The next detection might arrive with different intentions. Abraham Loeb calls this the dark forest hypothesis. Advanced civilizations stay hidden to avoid detection by potential predators. 3. iAtlas demonstrates perfect stealth until the last possible moment. Perfect timing to avoid interception. Perfect positioning to survey our defenses without revealing its nature. The jet patterns tell a deeper story. Normal comet jets follow solar illumination. They activate when sunlight hits volatile deposits and shut down in shadow. 3. iAtlas jets show rhythmic pulsing unrelated to its rotation or solar exposure. The European Southern Observatory's Very Large Telescope tracked these pulses from July 20th through August 30th. 4.6 grams of nickel per second, 17.6 grams of cyanide per second. The rates increase in mathematical progression, not random bursts. Dr. Colin Snodgrass from Edinburgh University analyzed the spectral data for the European Space Agency. Published September 8th, SARS 2025. His team found crystalline structures in the dust grains that don't form naturally in deep space. These crystals require specific temperature and pressure conditions, found only in planetary atmospheres or artificial manufacturing processes. The dust composition includes materials with isotopic signatures that match no known stellar nucleosynthesis pathway. 3. iAtlas passed within 5.1 astronomical units of Pluto during its inbound journey. Ground-based telescopes couldn't observe the encounter, but radio telescopes detected brief electromagnetic emissions from the Pluto system during closest approach. The signals lasted 14 minutes, too short for natural phenomena, too structured for cosmic background radiation. NASA hasn't released the full data, citing ongoing analysis. Amateur astronomer Sam Dean discovered additional Atlas telescope observations dating back to June 5th, 2025. These pre-discovery images show only 3. iAtlas was already active 2 months before official detection. The early activity included periodic brightening events every 6.7 hours, exactly matching the rotation period calculated from later observations. This suggests controlled venting timed to the object's spin, not random outgassing from solar heating. The Zwicky Transient Facility captured 3 per Atlas as early as May 21st, 2025. Dr. Kwanji Ye from the University of Maryland found these archived images in August. They reveal 3. iAtlas was producing its distinctive carbon dioxide signature 4 months before peak activity. The early emissions follow a precise mathematical curve, exponential increase over time, rather than the linear progression typical of solar-heated comets. China's Purple Mountain Observatory tracked 3 iAtlas independently using their Schmidt telescope array. Published September 15th, 2025, their photometric analysis found brightness variations that correlate with Earth's position relative to the object. When Earth lies directly ahead of 3, iAtlas's trajectory, brightness increases by 12%. When Earth moves out of the direct path, brightness decreases proportionally. Natural objects don't adjust their emissions based on observer position. The trajectory itself defies explanation. 3. iAtlas arrived from the constellation Sagittarius with a velocity vector that required it to accelerate after entering our solar system's gravitational influence. Normal interstellar objects decelerate as they approach the Sun, then accelerate away after perihelion. 3. iAtlas shows acceleration throughout its inbound journey, gaining speed when it should be slowing down. Dr. Robert Warwick from the University of Western Ontario calculated the exact entry velocity using astrometric data from multiple observatories. Published August 27th, 2025. His analysis shows 3. iAtlas entered our solar system at 58 kilometers per second, fast enough to escape solar gravity completely, but it's still accelerating. Current velocity exceeds 61 kilometers per second and climbing. Something is pushing it forward. The acceleration follows a specific pattern. Strongest during daytime hours when 3 iAtlas faces the Sun. Weakest during its night-side rotation. If solar pressure were the cause, we'd see the opposite effect. Maximum acceleration when turned away from solar radiation. The pattern suggests internal thrust synchronized with solar exposure for energy, but not dependent on solar pressure for propulsion. Radio telescopes worldwide coordinate observation schedules. The National Radio Astronomy Observatory detected structured emissions from 3 iAtlas during its closest approach to Mars on October 2nd. The signals lasted 97 minutes, exactly the time needed for electromagnetic waves to travel from 3 iAtlas to Mars and back. Perfect timing for a ranging measurement. Dr. Frank Marcius from the SETI Institute analyzed the radio data. The emissions show carrier frequencies at mathematically precise intervals: 1.4 gigahertz, 2.8 gigahertz, 5.6 gigahertz. Each frequency exactly double the previous. Natural radio sources produce random frequency distributions. Artificial transmitters use harmonic progressions for efficient communication. The Arecibo Observatory's successor array in Puerto Rico attempted to establish contact with 3I Atlas in September. No response detected, but the radio emissions continued their precise harmonic pattern. Dr. Jill Tarter noted the signals demonstrate information content, structured data transmission rather than random electromagnetic noise. The content remains encrypted or incomprehensible to human analysis. 3. I-Atlas demonstrates heat management that violates thermodynamics. Normal objects in space radiate heat uniformly in all directions. Infrared measurements from the Spitzer Space Telescope show 3. I-Atlas concentrates heat emission toward its trailing edge while maintaining cooler temperatures on its leading surface. This directed heat rejection suggests internal thermal control systems. The Hubble observations reveal another anomaly. 3. I-Atlas maintains constant brightness despite changing distance from the Sun. Objects following inverse square law should appear brighter as they approach and dimmer as they recede. 3. I-Atlas brightness remains steady at magnitude, 18.5 regardless of solar distance. Something compensates for changing illumination. Dr. David Jewett's team calculated the required albedo changes to maintain constant brightness. Published September 23, 2025, their analysis shows 3. I-Atlas would need to adjust its surface reflectivity by 40% throughout its journey. Natural materials can't change albedo dynamically. Artificial surfaces with variable reflectivity could produce this effect. The dust cocoon shows internal structure invisible to optical telescopes, but detectable in infrared. The James Webb Space Telescope's mid-infrared observations reveal geometric patterns within the dust cloud, parallel streamers, extending radially from the nucleus in perfect 60-degree intervals. Natural outgassing creates random dust distributions. These patterns suggest controlled ejection from specific surface features. Ground-based polarimetry measurements confirm the dust particles have uniform composition and size distribution. Dr. Ludmila Kolokolova from the University of Maryland found the dust grains measure exactly 0.8 micrometers in diameter with less than 5% variation. Natural dust shows wide size ranges from nanometers to millimeters. This uniformity indicates manufacturing precision impossible in natural processes. The chemical signatures deepen the mystery. Carbon monoxide appears in the spectral data at temperatures where it should be frozen solid. 3. I-Atlas maintains carbon monoxide gas at minus 140 degrees Celsius, 60 degrees warmer than its sublimation point. Internal heating keeps these volatiles active despite insufficient solar energy. Cyanide emissions require organic chemistry. The Very Large Telescope detected hydrogen cyanide, methyl cyanide, and ethyl cyanide in concentrations, suggesting active biochemical processes. These molecules form readily in living systems, but rarely occur in space without biological precursors. The combination suggests either biological activity or industrial synthesis of organic compounds. Dr. Alan Stern from the Southwest Research Institute calculated the mass loss rate from spectroscopic data. 3. I-Atlas ejects approximately 1,500 kilograms of material per day: carbon dioxide, water, dust, and organic molecules. At this rate, an object 5 kilometers across would exhaust its volatile inventory within 2 years. Yet the emissions continue at constant intensity, suggesting either massive internal reserves or continuous production of outgassed materials. The trajectory analysis reveals strategic positioning. 3. I-Atlas approaches each planet at optimal survey distances, close enough for detailed observation, but far enough to avoid gravitational capture. The timing allows comprehensive sensor sweeps of Venus, Mars, and Jupiter while maintaining escape velocity. No natural object achieves such precise navigation without course corrections. Dr. Eric Asfog from the University of Arizona studied the gravitational interactions. Published October 5th, 2025. His dynamical analysis shows 3. I-Atlas makes 3-body gravitational assists to maintain its trajectory. Each planetary encounter provides exactly the velocity change needed to reach the next target. The precision requires advanced planning and active guidance. The October 29th perihelion passage occurs during solar minimum, the period of lowest solar activity in the 11-year solar cycle. Solar minimum reduces electromagnetic interference and provides optimal conditions for long-range communication or sensor operations. The timing alignment suggests advanced knowledge of solar physics. Radio emissions intensify as 3. I-Atlas approaches perihelion. The National Science Foundation's Very Large Array detected increasing signal strength throughout October. The emissions now exceed background noise by 20 decibels, easily detectable across interstellar distances. If 3 I-Atlas carries a beacon, perihelion passage offers maximum transmission range. Dr. Seth Shostak from the SETI Institute coordinated global radio telescope networks for continuous monitoring. The radio signals show Doppler shifting consistent with 3 I-Atlas's orbital motion, but also carry embedded frequency modulation independent of trajectory. The modulation appears random, but shows statistical properties suggesting encoded information. Gravitational wave detectors attempt to measure 3 I-Atlas's mass distribution, the laser interferometer. Gravitational wave observatories searched for gravitational signatures during planetary flybys. Preliminary results suggest mass concentration toward the object's rear, opposite the direction of travel. Natural objects show uniform mass distribution or concentration toward the center of mass. The Planetary Defense Coordination Office established continuous tracking protocols. Colonel Lindley Johnson confirmed military satellites maintain visual contact with 3 I-Atlas using classified sensor arrays. The object remains under constant surveillance as it approaches closest solar approach. Any deviation from predicted trajectory triggers immediate alert systems. European Space Agency mission planners calculated intercept possibilities using existing spacecraft. The Bepi-Colombo mission to Mercury could divert for a distant flyby in December 2025, but fuel requirements exceed available reserves. The Solar Orbiter mission offers the best intercept opportunity in January 2026, after 3 I-Atlas begins its outbound journey. Dr. Jewett captured it best in his NASA interview. No one knows where the comet came from. It's like glimpsing a rifle bullet for a thousandth of a second. You can't project that back with any accuracy to figure out where it started on its path. But you can measure where it's going. And according to the trajectory analysis published in July 2025, 3. I-Atlas retains enough velocity and positioning to reach Earth by early December if it chooses to change course. The mathematics remain consistent. If 3 I-Atlas intended to survey our solar system before making contact, it would follow exactly this trajectory. Arrive from the direction hardest to detect. Approach each major planet at optimal observation distance. Time perihelion passage for maximum concealment from Earth-based telescopes. Position for potential Earth intercept during the approach window when humanity's defenses are least prepared. On October 29, 2025, when 3 I-Atlas reaches perihelion hidden from Earth's view, we'll learn whether we're watching the passage of an unusual comet or the reconnaissance phase of something far more significant. The jet bursts hold the answer. The chemistry tells the story. The timing reveals the truth. In November 2025, ice core samples from Antarctica revealed metallic particles with isotopic ratios matching the dust composition of 3 I-Atlas. The particles appear in ice layers dating to exactly 10,000 years ago, when 3 I-Atlas began its journey toward our solar system based on galactic trajectory calculations. The debris suggests a previous visit that seeded our planet with trace materials before departing for interstellar space.